Let's work on a least square problem. So we want to give the line of best fit for the paired data below. We have distances that people commute, 19537 measured in miles, and the gas that they use per week, 1543 and 2. So that's paired data. It's measured in gallons. We want to find the regression line or the line of least squares or the line of best fit. These are all names for the same thing. That predicts the gas consumption given the commute distance. We want to then use our linear model to predict the gas usage of someone who commutes 15 miles for work. So I want to create a regression line that predicts gas consumption. So the second data set there, the gas used per week, I want to let those be my Y values. Right? Because I'm looking for Y is equal to mx plus b, right? Every straight line in the Cartesian plane looks like that. And I want to predict my Y values, right? I want to feed it an X value, and then I want this equation to return a Y value. So I want these Y values right there to be the gas consumption because that's what I want my regression line to predict for me. So my Y values, my output of the function should be gas. So I have 1, 5, 4, 3, and 2. And the corresponding paired data, so the x's here, what I'm going to feed into the function will be the commute distances. So 1, 9, 5, 3, and 7. All right, so as we're trying to build this regression line, I need to find the m and the b. And the equations are m is equal to n, the number of data pairs, times the sum of the product of x and y minus the product of the sums. And then I divide that by n times the sum of the x squareds minus the square of the summed x's. So if you already know your correlation coefficient, you can note that this numerator is the same numerator as your correlation coefficient. So you don't have to reinvent the wheel. You don't have to find that numerator again. You should already have it. And you also know that this denominator is also present in your Pearson correlation coefficient equation. So if you already did your Pearson correlation coefficient, then solving for m is quite straightforward. You really only have to perform this new division because you already have your numerator and your denominator. But let's imagine that we haven't gone through that yet. We don't have our Pearson correlation coefficient, and let's compute our m. So I'm going to do a table again. I see a bunch of sums inside this equation that I need. So I need the sums of x's. I need the sums of y's. I need the sums of xy's. And I need the sums of x squareds. So note, it's a little bit different from your Pearson correlation because you don't need the sums of the y squareds. So you don't need those. For our x's, remember x data is the gas used per week. Oh, I'm sorry, x data is the commute distance. So that would be 1, 9, 5, 3, 7, which gives us a sum of 25. The y data, which is the gas used per week, is 1, 5, 4, 3, and 2, which gives us a sum of 15. The xy's would be 1, 45, 20, 9, and 14, which gives us a sum of 89. And the x squareds will be 1, 81, 25, 9, and 49, which sum to be 165. So we go back to this equation. How many data pairs do I have? What's my n? I've got 1, 2, 3, 4, 5 data pairs. The sum of x times y's, 89. The sum of x's, 25. The sum of y's, 15. In here, again, 5. The sum of x squareds would be 165. And the square of the summed x's would be 25 squared. So when you do this, you find a slope, and we'll have to estimate here, of about 0.35. All right, so that's our slope, 0.35. Now to figure out this b, the y-intercept of our straight line. So b has a similar equation as your slope. It's given to us by the sum of the y's times the sum of the x squareds minus the sum of the x's and sum of the products divided by the exact same denominator as our slope, n times the sum of the x squareds minus the square of the summed x's. So if you've already done this denominator right there, then it's the same thing down here. But let's imagine that we're doing this before we found m. So let's do this from scratch. The sum of the y's is 15. The sum of the x squareds is 165. The sum of the x's is 25. The sum of the xy's is 89. And then I divide by the same denominator as my slope. So I have 5 times 165 minus 25 squared. So when you do this, you find that you have a y-intercept of about 1.25. So our y-intercept now is 1.25. So our straight line right now, y is equal to mx plus b, is 0.35x plus 1.25. And remember, these y values are gas consumption. These x values are commute times. So I can use this. So the second part of this problem asked me to make a prediction using my linear model. Use our linear model to predict the gas usage of someone who commutes 15 miles for work. So what happens when x is equal to 15? You get 0.35 times 15 plus 1.25. That's going to give you about 6.5. And remember, your y, this model predicts gas usage. So this would be measured in gallons. So using our model, if somebody drove 15 miles to work every day, we would expect them to use about 6.5 gallons of gas per week based on our data.